scientists digging into the dust tail of interstellar comet 3 I/ATLAS just hit a serious curveball. What they found wasn't small, fast-moving debris like everyone expected, but massive dust grains drifting out at a crawl, almost like they're fighting gravity itself. That slow-motion behavior instantly raised eyebrows and forced researchers to rethink where this comet came from and how it was built in the first place. Before jumping deeper, let me slow it down for a second. Drop a comment telling me where you're watching from and what time it is on your side of the world. That kind of feedback really helps paint the bigger picture of who's tapped in right now. Now let's get into why this dust tail discovery around 3 I/ATLAS has scientists talking non-stop. When 3 I/ATLAS was first spotted on July 1st, 2025 by the ATLAS telescope in Chile, astronomers immediately noticed something felt off. The comet showed a thick coma, that hazy bubble of gas and dust around its core. But the tail? Almost non-existent. That's strange behavior, because most comets start flexing long, bright tails once sunlight heats them up and starts blasting material away. Normally, this process is automatic and fast. Ice turns to gas, dust gets shoved backward by solar radiation, and boom, a glowing tail appears. But 3 I/ATLAS didn't play by those rules. Its tail took weeks to finally show itself, only becoming noticeable by late August 2025. Data from the Gemini South Telescope revealed the anti-solar tail stretching about 30 arcseconds, roughly 56,000 kilometers. By mid-September, that number jumped to 50 arcseconds, close to 100,000 kilometers long. Slow start, but once it showed up, it kept growing. Dr. David Jewett from UCLA and Dr. Jane Liu dug into Hubble images from July 2025 and dropped a key insight. They explained that the delayed tail wasn't about timing, it was about the dust itself. The dominant dust grains measure around 0.1 millimeters, about the width of a human hair, and they're drifting off the comet at shockingly low speeds. That kind of behavior doesn't happen by accident, and it changes everything we thought we knew about this object. About 5 meters per second. To put that into real-world terms, that's barely faster than someone power walking down the street. These dust grains aren't flying off dramatically, they're creeping away, moving slow and heavy, and that sluggish motion says a lot about what they're made of. Smaller, lightweight dust would have been blasted away instantly, creating a tail almost on sight, but that didn't happen here. Instead, these oversized particles drag their feet. Because they're big and dense, solar radiation barely nudges them, so they hang around the nucleus way longer than expected. That slow escape is the reason the tail took so long to form, and it's a huge clue about the comet's internal makeup. According to the analysis by Jewett and Liu, tiny micron-sized dust grains might still exist in the coma, but they're not calling the shots. There just aren't enough of them to dominate how light scatters off the comet. What we're actually seeing are the heavyweight grains doing all the visual work. So where did the small stuff go? Researchers point to something known as interparticle cohesion. In simple terms, tiny dust grains stick together way easier than big ones. Over time, they clump up, forming thicker, heavier chunks instead of staying separate. It's similar to how snowflakes collide and lock together, building larger clumps instead of floating solo. What's wild is that this isn't the first time scientists have seen this pattern. Back in 2019, the interstellar comet 2 I/Borisov showed the same dominance of roughly 0.1 millimeter grains. That pattern hints that chunky dust might be standard for interstellar visitors, not just a one-off situation. But here's where 3 I/ATLAS really separates itself. Its dust production rate is on another level. During July and August of 2025, it was shedding around 180 kilograms of dust every single second at 2 astronomical units from the Sun. Borisov, by comparison, was only dropping about 70 kilograms per second at the same distance. That's more than double the output. Hubble data from July backed this up hard. Scientists estimated about 6 kilograms per second of small dust particles versus roughly 60 kilograms per second of large ones. The big grains completely dominate the scene. And as if that wasn't enough, fresh spectroscopic data from the James Webb Space Telescope revealed an unusually high carbon dioxide to water ratio in the coma. That chemical imbalance adds yet another layer to the mystery surrounding 3I/ATLAS. The ratio came in at about 8:1, and that's wild by comet standards. That's one of the highest carbon dioxide to water ratios ever recorded in any comet, period. Most comets from our solar system are straight-up water ice machines, with CO2 barely making a cameo. But 3I/ATLAS flips the script completely, with carbon dioxide running the whole show. In this case, CO2 isn't just present, it's driving the activity. Dr. Avi Loeb from Harvard University and his colleague Eric Quito laid out a detailed model explaining why this happens. As 3I/ATLAS drifts closer to the sun, temperatures don't just rise, they spike fast. That rapid heating cranks up sublimation, and since carbon dioxide turns from ice to gas at much lower temperatures than water, it starts escaping first, and in huge amounts. That extreme CO2 dominance sends a loud message about where this comet was born. Carbon dioxide ice doesn't survive just anywhere. It forms and sticks around in brutally cold regions, far away from stars. That points to 3I/ATLAS forming in the outer edges of its home planetary system, where temperatures stayed low enough for CO2 to remain frozen and untouched for billions of years. More clues came from spectroscopic data collected by the Southern African Large Telescope and the Nordic Optical Telescope. Scientists detected a slight reddening in the comet's reflected light spectrum. The spectral slope measured about 22.8% per micrometer in the optical range, which lines up with organic-rich material. That kind of reddening looks a lot like what we see in comets from the outer zones of our own solar system. It hints at complex carbon-based compounds baked into the surface long ago. And then there's what wasn't seen, which might be even more telling. Early observations showed a noticeable absence of emission lines from common molecules like C2, NH2, and CN. Those usually pop up loud and clear in active comets, but here they barely showed up at all. That suggests the outgassing isn't the usual chemical mix, it's heavily tilted toward carbon dioxide. And during July and August of 2025, astronomers spotted one more strange detail. The coma looked stretched westward in the sky, pointing toward the sun instead of trailing away from it. That backward-looking shape added yet another layer of mystery to an already strange interstellar visitor. This wasn't a tale in the classic comet sense at all. What astronomers were seeing was a raw dust plume blasting straight off the sunlit side of the nucleus. As 3I/ATLAS slowly rotated and sunlight cooked different surface regions, dust shot out unevenly, mostly from the side facing the sun. It looked strange, but it wasn't random behavior. This same sun-facing dust action has been spotted before in distant comets, like C2014 UN271, better known as Bernardinelli-Bernstein. These objects tend to stay quiet on the dark side while going active on the lit side, creating an off-balance, lopsided coma that looks stretched and uneven in telescope images. By late August 2025, things started to shift. The coma of 3I/ATLAS stopped leaning toward the sun and finally formed a clean anti-solar tail pointing away like a textbook comet. But the weirdness wasn't fully gone yet. Images taken on August 26th showed that the inner coma, within about 5 arcseconds of the nucleus, still looked fan-shaped and brighter on the sun-facing side. That change tells a deeper story. Early on, gas pressure from sublimating ice pushed dust straight off the surface. As the comet moved closer to the sun and activity ramped up, solar radiation pressure took over and started sweeping dust backward, shaping the familiar tail structure we expect. This dust analysis is doing more than just explaining visuals. It's exposing what interstellar material is really like. The large grain sizes and slow ejection speeds suggest the nucleus of 3I/ATLAS is tightly bound and surprisingly tough. While many comets crack, shed pieces, or fall apart under heat, this one held its shape the entire time. That kind of durability says a lot. It points to a solid, cohesive object that isn't fragile or loosely packed. Pair that with the extreme carbon dioxide dominance, and it screams cold origin, likely far out in the frozen outskirts of a planetary system billions of years ago. The reddish, organic-rich signature in the spectrum backs that up even more. Those complex carbon compounds look similar to material found in the outer solar system. And here's the real mind-bender. 3I/ATLAS is estimated to be about 4.6 billion years old, roughly Earth's age. It's been drifting through interstellar space most of that time, carrying a frozen snapshot of another star system's early history. The similarities between 3I/ATLAS and 2I/Borisov are hard to ignore. Both show dust grains on the larger side, which hints that chunky particles might be the norm for interstellar comets, not the exception. That pattern likely traces back to how dust grows and sticks together in the cold outer zones of protoplanetary disks around young stars, where material clumps up instead of breaking apart. Astronomers are still tracking 3I/ATLAS as it makes its exit. The comet passed its closest point to the Sun on October 29, 2025, and now it's cruising back toward deep space. By mid-2026, it'll fade out completely, too dim for even powerful telescopes to catch. Once it's gone, that's it. No second chances to study this visitor up close. What scientists pulled from this dust tail analysis is huge. Large, slow-moving dust grains around 0.1 millimeters in size, a tail that took its time forming, an extreme carbon dioxide to water ratio, and a surface rich in organic material. All signs point to one thing. This comet was born in a brutally cold, distant environment around another star billions of years ago. Its behavior lines up with comets from the far edges of our own solar system, but the details don't quite match. Those differences are the fingerprints of its interstellar origin, shaped somewhere else long before our Sun even had planets locked in place. If this discovery caught your attention, jump into the comments and tell me what part blew your mind the most. And seriously, where are you watching from, and what time is it there right now? I always like seeing how far the StellarDrift community reaches. Make sure to like the video if you got value from it, share it with anyone who's into space mysteries, and subscribe to the StellarDrift channel so you don't miss what's coming next. I'll see you on the next one.